All right, listeners, buckle up. Today we're diving headfirst into a topic that's, well, pretty fundamental to how we build software. It's object-oriented system development.
Oh yeah, this one's a classic.
Definitely a cornerstone.
Uh-huh.
Ever tried building something complex, like, say, a Lego castle, without sorting the bricks first?
Talk about a recipe for disaster.
Total chaos. Well, that's kind of what software development was like before OSD came along.
It really was a bit of a Wild West back then.
Right. Imagine trying to track down a single blue brick in that mountain of unsorted Legos. That's kind of what it was like trying to find a specific piece of code in those early systems.
You're not kidding. It could get really messy, really fast.
So we've got a mountain of research here, academic papers, textbook excerpts, you name it all, about how OSD came to the rescue.
It's a game changer, for sure.
Totally. So let's break this down. What exactly is object-oriented system development?
In a nutshell, it's about building software systems as collections of interacting objects. Each object has its own data and functions, kind of like those individual Lego bricks.
Okay, so instead of one giant block of code, we've got these smaller, more manageable objects.
Exactly, and those objects can interact with each other in defined ways to create a complete system.
Makes sense. But how do we ensure these objects don't just create more chaos? Our research mentions these four guiding principles: abstraction, encapsulation, inheritance, and polymorphism. Those sound a bit intimidating.
They do, don't they? But honestly, they're more intuitive than they sound.
All right, let's hear it. Let's start with abstraction. What's that all about?
Imagine you're using your favorite music app. You don't need to know how the app is finding songs or streaming them, right?
Right, I just care that it works.
Exactly, that's abstraction. It hides those complex details behind a simple interface. You just focus on what the object does, not the nitty-gritty of how it does it.
Okay, so abstraction is about simplifying things for the user. Makes sense. But what about encapsulation? That one sounds a bit more, I don't know, scientific.
It's all about boundaries and protection. Think of encapsulation as putting those inner workings of an object, the data and code, into a protective capsule.
Like a little safe.
Exactly. Other objects can't just mess with those internals directly. They have to interact through well-defined methods, kind of like a dedicated communication channel.
So encapsulation sets up rules for how objects interact, preventing them from interfering with each other's data.
Hmm.
Got it. Now, inheritance, this one makes me think of family trees.
Right on the money. Inheritance lets us create new objects based on existing ones, like a parent object passing down its characteristics to its children.
So if we have a employee object, we could create manager and intern objects that inherit all those basic employee properties.
Exactly. They get those core attributes, but can also have their own unique data and functions.
That's super efficient. No need to reinvent the wheel every time. Okay, last but not least, polymorphism. This one sounds a bit trickier.
It's really about flexibility. Imagine a button in an app. Depending on where it is and what it's connected to, that button might look and behave differently.
Ah, so the same button can do different things in different contexts.
Precisely. Polymorphism means many forms. An object can take on different roles depending on the situation.
I'm starting to see the power of these four pillars. They really do work together to create a more organized and adaptable approach to software development.
Absolutely. They're the foundation of everything we're about to explore.
So we've got our building blocks, these objects, but how do we actually design and build complex software systems using these principles? I see something about modeling and diagrams in our notes.
You're right. We don't just start coding randomly. Modeling is crucial in OSD. It's like creating blueprints before building a house.
That makes sense. But there are so many different types of diagrams mentioned here. Class diagrams, object diagrams, use case diagrams. It's a bit overwhelming.
Don't worry, each one serves a different purpose. Think of them as different blueprints for different aspects of your Lego castle.
Okay, I like that analogy.
Yeah.
So what are these different blueprints actually showing us?
Well, class diagrams, for instance, show the types of objects in our system and their relationships. It's like a family portrait.
A family portrait of objects. I'm intrigued.
Exactly. And then you have object diagrams, which are like snapshots of those objects at a specific moment in time.
So if the class diagram is the family portrait, the object diagram is like a candid photo from a family gathering.
Haha, perfect analogy. And then we have use case diagrams, which capture how users interact with the system. It's like storyboarding a movie, visualizing those interactions.
Okay, so we're mapping out how users will actually experience the software. What about sequence diagrams? What do those show us?
Sequence diagrams illustrate the flow of messages between objects, kind of like a comic strip showing how they communicate.
And lastly, Activity diagrams.
Those map out the steps in a process, showing how the system flows from one activity to the next.
Wow, it's like having a whole toolbox of blueprints to make sure everything fits together perfectly. But creating these models must take a lot of expertise, right?
It does. And that's where specific modeling techniques come in. Our research highlights three big names: Booch, OMT, and Jacobson. They're like the master architects of the OSD world.
Master architects, that's a great way to put it. So, what are the key differences between these techniques? Do they each have their own specialties?
They do. Booch, for example, is known for being incredibly comprehensive and detailed.
So, it's like having those super detailed blueprints with every little nut and bolt labeled.
Exactly. OMT, on the other hand, really focuses on modeling objects and their relationships at the core building blocks of the system.
It's like focusing on the structural integrity of the Lego castle, making sure the connections are solid.
Precisely. And Jacobson is all about putting the user first, making sure the system is designed to be intuitive and easy to use.
So he's thinking about how the user will actually experience the Lego castle, making sure there are no hidden traps or confusing pathways.
That's a great way to put it.
With all these different techniques, though, it seems like things could get a bit, well, confusing. Is there a way to bring them all together? I keep seeing this term unified approach pop up.
That's a key concept. In the early days, it was a bit like having different construction crews speaking different languages.
Ah, I can see how that would lead to some serious miscommunications.
Definitely. So the unified approach aims to create a more standardized way of working, a common language for building software.
So like a universal translator for software development.
Exactly. It's about streamlining communication, collaboration, and the entire development process.
Wow, we've covered a lot of ground. From objects and principles to modeling techniques and this unified approach, I'm already starting to see the power and potential of this object-oriented world.
And we're just getting started.
All right then. In the next part of our deep dive, we'll explore how these seemingly abstract concepts translate into real-world software. Get ready to see how object-oriented system development shapes the applications we use every day.
It's going to be fascinating. Welcome back. We've delved into those core principles, modeling techniques, the whole foundation of OSD. Now, let's see how they come to life in actual software applications. You know, the ones we all use every single day.
I'm all for some real-world examples. We've been talking Legos and blueprints, but I'm ready to see those bricks assembled into a real castle. Our notes mention component-based development. Is that where a Lego analogy really shines?
It absolutely is. Think of component-based development, or CBD, as those pre-built Lego sets. You know, the ones for a castle, a spaceship, you name it. Each set is self-contained, got all the pieces and instructions you need.
So you can mix and match those sets to create even bigger, more elaborate creations. Instead of building every single detail from scratch, you're using these ready-made components that have already been designed, tested, the whole works.
Exactly. In CBD, developers use these pre-built software components. They can be small pieces of code or entire libraries even. And they assemble those into a custom solution. Think of it like a buffet of proven solutions. You pick and choose the components you need, assemble them into this, well, delicious software feast.
Okay, I'm following you.
Sure.
But can you give me a real-world example, something I might actually use every day?
Think about Google Maps. When you use a Maps app, you're benefiting from CBD. The app isn't building the entire mapping system from scratch, right?
Oh, of course not.
It's using Google's pre-built mapping components. You've got the maps themselves, the search function, navigation, all those tools. Google has made those available to developers through what's called an API.
Wait, an API? That sounds familiar, but I'm not sure I entirely get it.
API stands for Application Programming Interface. It's essentially a set of rules that allow different software systems to talk to each other. Think of it like a universal translator, helping apps use those pre-built components from different sources.
So the Maps app is using Google's API to access those ready-made mapping components. Clever. The app developer doesn't need to reinvent the wheel, and I get a seamless mapping experience.
Exactly. And CBD is everywhere. Look at e-commerce websites. Many use pre-built components for shopping carts, payment processing, shipping calculations, you name it.
Wow, it's like CBD is the silent hero behind so many apps I use every day. This whole object-oriented approach seems all about efficiency and reusability.
It is, but it's also about speed and adaptation.
Yeah.
Our notes mention something called Rapid Application Development, or RAD. It's a methodology that really embraces change and rapid prototyping.
RAD. Sounds a bit intense. Are we talking software that builds itself at warp speed?
Not quite warp speed, but definitely about accelerating development. With RAD, you don't spend months perfecting every detail before releasing the software. You build a basic version, get it into users' hands quickly, gather their feedback, and then improve based on that feedback. Think of it like building a prototype spaceship before launching the full-fledged mission. Test, adjust, refine.
So it's less about rigidly sticking to a plan and more about being flexible, responding to what users actually need. Makes sense in today's world where everything moves so fast.
Exactly. And RAD aligns perfectly with the object-oriented approach because those modular components can be swapped, updated, rearranged based on what users are saying.
This is all making so much more sense now. It's like all the pieces of the puzzle are clicking into place. We've got our building blocks, our blueprints, and now these methods for assembling and refining the final product. But our notes keep coming back to this unified approach. What exactly does that mean? Is it like some grand unifying theory of software development?
Not quite a grand theory, but definitely a move toward a more standardized and integrated way of working. In the early days of object-oriented programming, it was a bit of a free-for-all. Everyone had their own favorite methods, notations, tools, like trying to build a house with a team of architects who all speak different languages.
Yeah, I can imagine that would lead to some serious communication breakdowns.
You said it. So over time, there's been this push to create a more unified approach, standardizing things like modeling languages, design patterns, development processes. The goal is to make it easier for developers to talk to each other, collaborate, and build software that's more consistent, easier to maintain.
So it's like establishing a common language for building software no matter what specific tools or techniques are being used.
Exactly. And one of the key elements of this unified approach is the Unified Modeling Language, UML. Remember we talked about that earlier?
Yeah, the standardized way to visualize software design.
Right. UML provides that standardized way to represent the system no matter what specific methodology you're using. It's like having a Rosetta Stone for software development.
Love that analogy. But UML is just one part of this unified approach, right?
Well,
What else is involved?
another important piece is design patterns. Remember those pre-solved problems we discussed. Design patterns are essentially blueprints for tackling common software design challenges. They're not specific pieces of code, but more like templates or guidelines that you can adapt.
So it's like having a recipe book for software design. Instead of starting from scratch every time, you can use these tried and true recipes.
Precisely. By using established design patterns, developers save time, avoid common pitfalls, and create software that's easier to understand and maintain.
This unified approach sounds really powerful. It's like bringing order to what could be a very chaotic process. But how does it work with those different process models we talked about? Waterfall, incremental, spiral, all those. Are they compatible?
That's the beauty of the unified approach. It's not tied to any specific methodology. You can use it with waterfall, incremental, spiral, whatever fits the project. It's a versatile framework that enhances communication and collaboration, regardless of the specific process you're using.
So it's like having a universal set of tools that you can use in different workshops, regardless of the specific project you're working on, bringing clarity and consistency to the overall process.
Exactly. And that brings us to an exciting point in our deep dive. We've explored the foundational principles, the modeling techniques, and now this unifying approach. But the world of software development never stands still, right? There are always new trends emerging. What's next for object-oriented system development? What's on the horizon?
Now that's a question I'm eager to hear the answer to. It seems like every day there's a new technology or buzzword in the tech world. So what's next for this object-oriented approach? What's the future hold? Okay, so we've been through the theory, the models, even this quest for a unified approach. But with all this talk about objects and blueprints and whatnot, how does this actually play out in the real world? Like what kinds of software are built using these principles?
Well, object-oriented system development has touched just about every type of software we use today.
Really? I mean, I can see it for apps and websites and things like that, but what about the deeper stuff? Like the stuff that runs my computer?
Oh, absolutely. Our sources go into this fascinating range of applications. They start right at the foundation, actually system software.
System software. So that's like operating systems, right? And all those things I rarely see but totally rely on, like compilers.
You got it. Think of it as the behind-the-scenes crew that keeps your computer running smoothly. It's interacting directly with the hardware, managing memory, files, program execution, the whole shebang.
So even those complex, low-level systems are built using these object-oriented principles. That's pretty impressive.
It really is. It helps keep things organized and efficient, even at that fundamental level. But then you have, of course, All the software we interact with directly applications.
Right, like business applications, those engineering and scientific programs that crunch massive data sets, those are all OSD too.
Exactly. From inventory management systems to financial analysis tools to those high-powered scientific simulations, OSD is everywhere. It's pretty amazing how the same principles can be applied to such a diverse range of software.
It really speaks to the power and flexibility of this approach.
It does. And as technology advances, those lines are getting blurrier. We're seeing real-time interactive features in scientific software, complex algorithms embedded in everyday apps. It's all converging.
That's fascinating. And our notes also mentioned embedded software. What exactly does that mean?
Embedded software. That's the software that lives inside all sorts of devices, controlling their functions.
Oh, I see. So like the software in my microwave or in a car's braking system, even a digital watch.
Exactly. It's often hidden from view, but it's absolutely essential. And as those embedded systems become more complex, object-oriented principles become even more crucial.
Makes sense. Our sources also talk about product line software. Is that related to the component-based development we discussed earlier?
It is. Product line software is all about building a family of related products. They share a common set of features, but can be customized for specific markets or customers.
So, like car manufacturers building different models on the same platform. You've got a sedan, a coupe, an SUV, all using shared components, but with variations tailored for different preferences.
That's a perfect analogy. They're leveraging those pre-built components and customizing them for different applications. It's a really clever way to streamline development and cater to a wider audience.
Really efficient. And of course, we can't forget about web applications. Those are everywhere these days.
Absolutely. Web apps have transformed how we interact with software, and object-oriented principles are essential for building those robust and scalable platforms that can handle millions of users.
Makes sense. There's one more category in our notes that I'm a bit hesitant to ask about. Legacy software. It just sounds, well, old.
It does have a bit of an antique feel, doesn't it? Legacy software refers to those older systems that are often outdated, but still critical to many businesses.
So they might be written in older programming languages or be hard to maintain, like that vintage car that still runs but needs constant repairs.
That's a great way to put it. And dealing with legacy software can be a real challenge. Maintaining it is costly and risky, but replacing it can be even more disruptive. So there's this whole field focused on modernizing those legacy systems.
So using object-oriented principles to give those older systems a new lease on life.
Exactly. Whether it's rewriting parts of the system, migrating it to a newer platform, or integrating it with more modern applications, it's all about making those legacy systems more manageable and extending their lifespan. But even beyond these specific categories, there are some really exciting trends emerging that build on those object-oriented principles.
Okay, I'm all ears. Give me a glimpse into the future of software development. What's next?
Well, have you heard of model-driven development?
Model-driven development. Is that like creating a virtual model of the software before you actually read any code?
That's the essence of it. In model-driven development, or MDD, you create these higher-level models of the system using specialized languages and tools. They're like detailed blueprints that capture the system's design.
And then what? You can generate actual code from those models, like having robots in a software factory doing the coding for you.
It's kind of like that. MDD has the potential to really speed up development, reduce errors, and make software much more adaptable to change. It's still evolving, but it's definitely something to keep an eye on.
Sounds pretty futuristic. What else is shaping the future of software development?
Another big trend is service-oriented architecture, or SOA. It's a way of building systems as collections of loosely coupled services that communicate over a network.
So instead of one big application, you have a network of independent services working together.
Exactly. It makes systems more flexible, scalable, and promotes reusability.
And this SOA approach is compatible with object-oriented principles.
Absolutely. Those services can actually be thought of as large-scale objects, each with its own functions and interfaces. It's a natural fit.
Wow, it's amazing to see how those core concepts are being applied in all these new and innovative ways. It feels like we've only just scratched the surface.
I agree. And as technology keeps evolving, I have no doubt that object-oriented thinking will continue to be a driving force in shaping the software that powers our world.
This has been an incredible journey. I feel like I've gained a whole new understanding of how software is designed and built. Any final thoughts or takeaways you'd like to leave our listeners with?
I think the key takeaway is this. Object-oriented system development isn't just about coding techniques. It's a way of thinking, a philosophy, a way of approaching the entire process of building software. It's about breaking down complexity, creating adaptable systems, and always keeping the user in mind.
Well said. It's fascinating how something as technical as object-oriented programming can ultimately be about serving human needs and making our lives better.
Exactly. And that's what makes this field so exciting. It's about solving problems, creating value, making a positive impact.
Couldn't agree more.
Hmm.
Our listeners are walking away with a newfound appreciation for the worlds of object-oriented system development, I'm sure of it. Thanks for joining us on this deep dive. It's been a real pleasure exploring this fascinating world with you.